Okay, for our last session today, we have an old colleague of mine. We used to work together in the Java platform group at Oracle, and Monica is one of the cool performance engineers. Both of us have left, and Monica is doing her own company now, Code Karam, where she helps people with performance issues. Today, she's going to let us in on some of the nitty-gritty details of contention in Java 9. So please welcome Monica Beckwith.
Cool. Hello. When I was thinking about a talk, I wanted to do something with Java 9, and I wanted to provide an insight as to how I would approach a performance problem. So, okay, so let's get started. So I'll tell you why I chose this particular JEP, okay? I'm Monica Beckwith, and I have my consultancy firm known as Code Karam LLC. And a little bit background, I worked with Oracle, and then most of my life as a performance engineer, I have done managed runtime. Okay, I started as a compiler engineer, but very quickly I moved to managed runtime performance issues. And I started with advanced micro devices, and then Sun, and then Oracle. At Oracle, my last title was garbage first, garbage collector performance lead. So that's me. So first I would like to present, set the stage, right? So why I chose this particular one. So we'll quickly look at the JEPs in JDK 9. And then we'll build a problem statement, because I want to show you how, say if it was given to you, improve contended lock performance, right? So if I was at Oracle and this was my JEP, what I would do, right? So then we'll move, so then I'll move into more information on performance engineering approach. So what do we choose? Which approach do we choose? Top down, bottom up? Usually, well, and I will talk more about that, but it's if you know the application or if you're working from the platform level. So choosing the right approach is very important, and then building your arsenal, building on that approach and getting your benchmarks and everything else done to make sure you're measuring the right thing is really important as well. And then fun things. Then we'll see how it all happens, right? So we'll perform analysis by comparing JDK 9 with JDK 8, and we'll summarize. So setting the stage, okay? So there are 89 total JEPs in JDK 9. So these are, okay, we'll just move it. There you go, ta-da. Okay, so now I have to look over there. So here are all the 89 JEPs, okay? Most of them, we know. I mean, there's some G1 related, some things are like JShell related, and most of them are functionality related. I already have a talk on G1, so I wanted to do something else. So I found, oh goodness gracious, I'm sorry. I'm very short, so for me to be able to see anything up there in the corner, it's near impossible, so. Alt. Oh, goodness. Maybe I should just mirror the display. Oh, yeah, how great is that? Thank you. I was just going to change it to mirroring the display, but there you go. This is so much easier now. Okay, so one of the JEPs, like I said, was contended lock improvement, okay? So what is JEP 143? So it brings about improvement to contended locks. You may have heard about locking improvements, prior to JDK 9, right? We know something about bias locking, right? But so the difference between that and this is bias locking is for uncontended logs, okay? And what does that mean? So that's where we talk about problem statement. So let's build a problem statement. The summary of JEP 143 mentions that we're going to improve the performance of contended Java object monitors, okay? Contended being the key here. So what does contention mean? So you have a synchronized method, and a single thread T is executing it, right? Everybody's happy. There's a single thread T on a synchronized method. There's no contention, okay? Now, a different thread U wants to enter the synchronized method, which is already locked by thread T. Now, this is contention. So bias locking was geared towards biasing the lock towards an uncontended, like a synchronized method or whatever, right? So you're trying to avoid the CAS, all right? So, but this is contention, serious contention, and we want to measure the contention and measure the improvements in the contention. So what that means is it is a heavyweight lock. So if you've heard OS terms like heavyweight or inflated locks, that's what this is. It's not your CAS. It is basically where you have object monitor, and the object monitor maintains a weight set. And I'll talk about what the weight set is. So it's a weight set for threads that want to get the lock. So for example, in our case, T already had the lock, and U wanted to get the lock, right? So then U goes in the wait set and waits to be notified. So if I had to draw something, this is what I would say. It's very simple. So you have the object monitor, there's an entry, there's an exit, and there's a wait queue. So everybody else who's not owning the lock is waiting in the queue. What is a wait set? It's a set of threads, as simple as that. It's created, the set of threads are there, and they're empty in the beginning, because of course nobody is contending for that monitor. And then you can only manipulate it by wait, which means now you have to go into wait, notify, that means you're able to come back and get access to the thread. So like every object has an associated monitor, and similarly an associated wait set. So when you have a monitor, you have a wait set. So if I had to now put this information in the previous, this is how it look. So when a thread has to go into wait, it'll go in the wait queue. Once you get either a notify or a notify all, it comes back and it can get to the object monitor. Okay. So this is basically the basic of a contended lock. Okay. Now let's talk about from the performance standpoint. So I mentioned there's top-down approach and there's a bottom-up approach. So I'm just want to give you a little overview of what that means. So let's start with top-down performance approach, okay? So what are you trying to achieve with top-down? You're trying to improve the application. So if I just had to draw a simple stack, it's a very simple stack, I'm trying to improve the application. So I'll try to go look at my platform as a black box. So anything below the application is a black box. So I'm trying to tune from the application and trying to work from there. So it's called the top-down approach. And the process for top-down is similar to what you may have seen or anywhere else. You monitor, you profile, you analyze, and then you tune and apply. And then you again monitor and make sure that everything that you just did is working to your need. Okay? Bottom-up approach. So what are you trying to achieve with bottom-up approach? You're trying to improve the platform. So what that means is that anything that's below the application is your platform. So in this particular case, I want to improve the lock, right? The object monitor. So I'm trying to, my platform becomes the JVM, right? So from the JVM point of view, I'm trying to build my arsenal, right? I'm trying to benchmark and do the analysis from JVM point of view, and I'll show you how we will do that, okay? So the approach is the same again. You monitor, you profile, you analyze, and tune and apply. So if I was still working for Oracle, I would have done the last step as well. But here, we're just going to stop at analysis to make sure that the performance is actually improved, because that job is complete and performance should have been significantly improved when we're comparing to JDK8, all right? So we'll stop at step 3. So choosing the right approach. Why do we choose bottom-up? Because we want to improve the platform. In this particular case, we want to improve the JVM locking performance. So that's what it says. So to do the bottom-up approach, you need the power to stress the platform. So you know what you want, but you don't have, so you're going to build up to getting there, right? So I want to stress the platform. The basic thing is that because I want to make sure that I'm doing an improvement to my platform, I want to stress that improvement, okay? So that's how you set up for benchmarking. So you start at the very beginning. Know what you're stressing, right? Once you know what you're stressing, then it's as simple as getting the right workload, or you write your own workload, right? Because you already know what you're stressing, okay? And then eventually, to do the analysis, you want to make sure that you have the appropriate tools, right? So again, you either write your own tools, or you get the appropriate tools. So let's start with know what you're stressing. So if I take you to the page, the JEB page, you'll see that these are the targets listed, and they're doing testing on that. And basically, these are the events, like parking and unpark is basically, park is basically, you're waiting for some kind of notification, like a trigger saying that you have to stay here till you're allowed to unpark, and then you can move ahead. So it's, if you have looked at other threads, even at OS level, it's kind of similar. And the monitor, enter, and exit is what I showed in the drawing. You have the enter and the exit, and the notify all was the wait queue. So these are the events related to contended locking. And we want to make sure that all these events are sped up on JDK 9 when you're comparing it with the JDK 8, right? So we have to individually make sure that these things are performing better than what they were at for JDK 8. So now next thing, so we know our stress, right? Now we need to get the appropriate workload. Again, because this is already done, what I chose one of the list of workloads that they had, and that is by Doug Lee. It was called Lock Loops, and now it's called Lock Loops JSR 166. And the benchmark does a lot of things. It compares a lot of locking techniques. But for our purpose, like I said, we need to measure contended locks, right? So we're going to use this section of the benchmark where it does built-in lock loop, and it's a JVM lock. And that's the thing that we want to measure. So we're measuring synchronized this, which is the instance, and we're measuring that. And this will keep it in basically that's what it does. It does it in a loop, and it adds multiple threads, so there's a lot of contention, okay? It's a very simple benchmark. Compute 1 and compute 2 are basically just some work to be done, so it doesn't get optimized out, okay? Now, another thing we have to do, because we know there are lots of improvements to locking that have been done. Remember I said we need the lock to be inflated. Why did I say that? Because I don't want to measure thin lock performance. I want to measure fat lock performance. I want to make sure it is in fact contended. We're going to measure deep contention. Again, I don't want to measure uncontended lock, so I want to make sure that bias locking is disabled. So that's what we need to do next. So when we do our measurements, we want to make sure that bias locking is disabled. So if you see, there's a minus use bias locking in my one of the options that I'll use. And the second option, I'm ensuring that I'm using heavy monitors. So when I do that, I make sure that I'm using object monitors, and then I'm making sure that they're contended, of course. So that's the the gist of the JEP is to make sure we're measuring contended object monitors, right? So we make sure that we use these options to measure the right thing. And finally, the tool, okay? So this is the tool that I have used for a long time now. Ever since I was at Oracle, and even now, past Oracle, I always measure. Let me go to the page. Okay, so I think there it is. All right, there you go. So this tool was started with as a C++ compiler, and then eventually they added Java, and this was like more than a decade ago. They added Java profiling abilities. And in the simplest form, it's samples, right? Clock profiling. And then you can also do hardware profiling, basically based on hardware events, right? So you can do event-based profiling versus clock-based clock profiling. So what we're going to do is just do simple, because we want to actually measure the improvements in those events, right? So we were just going to do clock-based profiling, okay? But if you get, and I have this link later on, please go and start using it and just play with it. This is the best application, code level profiling tool that I've ever seen. And it is very highly integrated with Java. So I'll show you the modes that you can use. And then if you use it, then go ahead and write to them. They'll be very happy. If you need any help, they would be very happy to help. And a very good team of expert tool engineers there at Oracle. So coming back to our presentation. So like I said, the collect tool is very simple. By default, -j on is on, which means it is available for Java profiling. By default, you have P on, which is, again, a clock profiling rate of 100 samples per second. Like I said, you could do heap tracing, you could do you can have a duration of how much. So if your run is about 10 hours long and you don't want to measure the entire 10 hours, because that may be adding a profiling overhead. So if you want to measure only a particular window, you could do that by specifying that on the command line. And then you can do various hardware counter profiling as well. In our particular case, we just use the default and we're happy. Okay. So let's talk about the targeted improvements again, okay? So we had these 4 that we wanted to see. The unpark event, the enter operation, the monitor enter, monitor exit, and then notify, monitor notify, okay? Oops, sorry. And then for that one, let's go quickly to this demo here. Sorry. So this is something that I already have, but let's start from the scratch here, right? So And you'll download this particular SSA tool, the Sun. It used to be called Sun Studio Analyzer, so I'm still calling it the same thing, but it's now called Developer Studio, so that's what it is. But they still have the SSA in the path, so that's funny. But here you go. So this analyzer is a part of that same tool, the collect and then analyzer, okay? And okay. Can you just duplicate it? Just the easiest. Let's duplicate it very quickly, because I don't want to drag it down. There you go. Awesome, thank you. So I'm going to go again. We're going to go here again. And I'm going to start the tool here. Okay. And this is the first screen that you see. And you have the options to create an experiment, which means that you're using the GUI to do the collect, the command line collect that I showed you. Okay. You could view experiments, which is what we're going to do because we've already collected the samples. And there's something that's called compare experiments. And that's what I'm interested in, actually. So I'll go ahead and compare experiments here soon, too. So let's just view an experiment first. And then here it tells you all the details of the experiment. So you see, I have it disabled. Let me just make it full screen. Okay, so it shows you that I'm testing logs, and then I've disabled bias locking, okay, and other things. And then you look at functions, and there's 3 different ways to view it. In the most basic form, it's all the user functions that you would know are here. So basically, all your library things are here. And then, of course, you cannot see any Java call stack. Neither can you see the JVM system, okay? And as you get more conversant with this tool, you would notice that eventually you would want to only work in the expert mode, or if you are very comfortable with machine code like assembly, which I am, and if you are going to be doing performance at the platform level, then you should be. Because if you're doing this bottom-up approach, you're basically dealing with the platform, right? So machine level, knowing assembly language becomes very critical for performance analysis from bottom up, right? So this is the expert mode, which kind of shows, if I showed you, we don't have to go into details of these things, but what I'm trying to show here are the things that this tool enables you to do. You could see the call tree here. You could go and look at the source if you select a function. Let's select a function then. Okay, and then you can look at the source here, right? And then you can look at the disassembly too. So here you can see the bytecode, right? Now, if I wanted to look at the disassembly in machine level code, so you just select machine level, and then again you go disassembly, and now, so you no longer see the bytecodes, you actually look at the assembly, which is like, this is a Linux system, so your x86 system, so you'll see assembly level at x86 assembly here, okay? Now, how does this help me? And then you can see caller callees, and you can keep on digging till you get to the place you want to be. And you could also, like I see, in the call tree, you can see exactly what was the root, if you wanted to see it in an advanced state like that. One more important thing here is the timeline function. So all your runs and whatever threads were running on the system at that time, it shows a timeline of those. And then you can zoom in to a particular thing, or you could just click on a small thing here, and it shows you all on the right-hand side. It'll show you the call stack for that particular event that happened and that was captured. Okay, so I have something already open here because I didn't want to spend too much time on comparing experiments. So we'll start at the beginning. So we'll talk about the experiments I'm comparing here, okay? So these are the experiments I'm comparing. Again, I have used bias locking disabled and heavy monitors enabled. So, and then I'm using lock loops, which is by Doug Lee, and I'm using contended, making sure it's heavily contended, okay? So this simple command line, okay? As it is, you can see when it's showing you the gray lines and the green lines, you can see that one is already better than the other. So baseline is JDK 9, and the comparison is JDK 8. So 100% is JDK 9, and then the other one is JDK 8. So already JDK 9 is performing better just in the time, because it was for the duration of the experiment. So JDK 9 was faster already. But we want to make sure it is due to contended log performance, right? So we're going to dive into deeper. I'm going to look at the functions here. Okay? So, and I'm going to go here quickly. So let's look at a platform event unpark, okay? So what is great over here is like you could find your method that you want. So I want to find unpark. Okay, we can just write everything here. Okay, so that one, the highlighted in blue, and let me explain what you see here. So, so left-hand side, you see exclusive. What that means is that it is just that particular, the time attributed to that particular method. So when we're looking at OS platform event unpark, on the left too, you have the baseline and the experiment 1. So my baseline, like I said, is JDK 9. Experiment 1 is JDK 8. And the right next to that is inclusive time. So if I had any calls from that particular method, and so those will be the inclusive calls. So when I do my call tree, anything that has been called from OS platform event unpark, all those methods, all the times will be collected together and shown in the inclusive time. So we not only see inclusive time improvement. You see, JDK 8 was 29 seconds, and JDK 9 is only 17 seconds. So we already see an improvement there. But that particular method by itself, that means exclusive time, is showing a lot of improvements too. It's 0.04 seconds compared to 0.94 in JDK 8. So when I'm gonna show and summarize this, we're gonna show that that particular method is improved. And we can dive into one of those methods here. I think we have time. So let's look at that. So let's look at the disassembly. Okay? And the reason, I'm not trying to scare you. The reason I wanted to show this is that if you see those orange things, those are the hot code, the hot instructions, right? And what we see is that right after exchange so your baseline has a hot instruction, which is because of that exchange. And then in your experiment 1, which is JDK 8, you have multiple hot paths. So you have the exchange instructions, of course, and there are others. So if I right here on the right-hand side, you can click here, you got that one, and then you can click here, and you have the other ones too. So there are a bunch of, there's a call that is also hot, and there are other things. So you can deep dive into it. When you use this particular tool, it kind of helps you identify these expensive instructions, okay? And in here, you have other things here, so like, let's look at that. So the generated code is a little different. It's a little bit cleaned up in JDK 9. Like if I had to do instruction by instructions, we could definitely see that. And so let's go back to the functions again, and let's look at the next one, which is object monitor enter, okay? So right here, so this is enter 1 and enter. Let's look at both of them. So you will see the inclusive time again. Let's look at enter. The inclusive time for JDK 8 was 372 seconds, and for JDK9 was 219 seconds. And that's inclusive and exclusive. Again, JDK9 was better. Just that particular method by itself, JDK9 is spending less time in it. So it has improved. Now looking at the source again, in disassembly again, you can see why. So if you sat down and compared the disassembly, and let's see if maybe we can get bytecode. Let's see if we can get bytecode. I'll have to go back to the functions. Oh yeah, so anyway, we'll talk about that later. So let's see if we get. Yeah, it doesn't show up because, yeah, there you go, exit. So let's try just the exit this time, and then let's see disassembly. Okay, it still shows the assembly level because at that time it only has, because it's an event that is a runtime event. So when we're looking at that, so if you look at your bytecodes and then you look at your runtime events, sometimes when you're doing profiles, it may get inlined or something else may have happened that it doesn't show you the bytecode, but it'll show you as a list of these instructions. But luckily, because we already know these hotspots, we can compare those and we can see the generated code. And then eventually you can use something like JITwatch or something. If you're really interested in optimizing the bytecode or learning how the bytecode was optimized, you look at JITwatch and open these two with JITwatch as well. So that's another thing that you could do. Or individually, you can just look at this without outside the comparison window. So if I open these experiments by myself, it would let me do that. But right now, it won't let me do it because we're in the comparison mode. So it has to sync the line number, so to speak. So it won't let me do that. Now we could go back to the thing, but I wanted to show you the timeline. So like I said, all the threads, I had so many threads, right? In my command line, you saw like 10,000 plus threads. So all these threads are here. And at any particular time, if I wanted to say I wanted to sync up my GC event, if I wanted to use this for stressing GC, right? So if I wanted to sync my, check out what happened at that particular GC event, so I would just click on that particular event and zoom in and look at the things happening at that event. So eventually, you'll zoom in so much that you'll see only these 4 things that happened at that particular time in the entire timeline. And then we could look at the call stack right here, and let's see what that is doing. So that was the code that I was testing, right? We were testing built-in locks, and that's what it is. It's whatever the code was we're testing. So that shows up there, right there. So all you have to do, you can also approach it from timeline point of view. What event happened? What was my program running at that time? And what was the most expensive code or whatever. So you'll see that in orange. Okay? If you have more questions, we can always go back to that. But I would like to continue. All right. So we saw the object monitor enter, and then the next, so these are my observations. Basically, I just copied those times that we saw, and I wrote down here. And then we did the exit too. So there were 2 things that I measured with object monitor. So if you look at the call stack, the exit and exit epilogue are in the call stack. So I wanted to measure both of them, and it does show improvement. Okay. So now that's the notify. So it's the same way. So I want to look at the other events, and I want to make sure those are faster. So I would like you guys to go and try this at home and get the, find out how to see if notify and notify all have improved as well. It's all shown in the method, in the experiment methods. All you have to do is look at that and compare it and figure out what changes were there made at the assembly level. Okay. I think we're pretty close to, yeah, okay. I'll leave some for questions. Okay, so this particular setup, there was some information that I told you about contented locking. I told you about synchronization. I spoke about bias locking, right, for uncontended locks, and some performance methodology. So all those things are the references. I don't say that I'm an expert on synchronization or any of those things. I have learned from these pages, and I encourage you guys to go read on them and learn from these pages. This is very common for anything you're testing, right? You need to understand the subject matter. You may want to make sure that you're testing the right thing. So if you don't do your groundwork, you may end up testing something else. So what if I didn't know the difference between contended and uncontended? And actually, I did not use heavy monitors, like enable heavy monitors from the get-go, and I didn't observe much difference in performance. Then I was like, well, something is not right, right? They have marked it as complete. That means something has happened. Why am I not able to measure it? And then I was like, okay, I gotta make sure that we're using heavy monitors. We have to make sure that you're disabling by. So these things you learn by trial and error, but the good thing is that you do your research and groundwork. So yeah, if you're interested in contented lockings, please go ahead and read those. And I think that concludes my presentation. I'm open for questions. Any questions? It doesn't have to be contented locking.
How do you collect the experiment?
So the collect tool, so I did by command line. Okay, I may have it here. This is the benchmark, so let's see if I have it here. And the reason I'm going between laptops is because this is a Mac, and that is a Linux-based laptop. I do most of my stuff here, and also the studio tools work on Linux and Solaris. Okay, so they don't work on Mac, so I have to use this. So let me show you. So let's see, let me get back here. Okay. Do I need to set it again? Display. Let me try again. Oh, there you go. Good. So anyway, so you see right here, all I had to do is make sure that I have the collect tool in my path, and so. So this particular line, I just said J on. Even actually, now, because it's so advanced, you don't even have to say J on. But since I have a habit of doing that. But J on just means it's a Java program. So you just have to do that. So it's basically the collect tool, and all I had to do is J on. I ran it for the entire duration of my experiment, and then I provided the heavy monitor enabled and bias locking disabled, and that's it. And then the test, the actual benchmark. So it's as simple as that. You could also do it from, like I said, from the GUI itself. So if you start the analyzer GUI, which is also very simple, it's simple. So the collect tool, the analyzer tool are all in the bin directory. And you start the analyzer GUI, and from within the analyzer, you can launch your, any of the profilers that you may have used, or any of the, even when you write a micro benchmark and you want to do a quick run, you use any GUI, any of your favorite GUIs, Eclipse or whatever. So you would launch it from the GUI itself. You can do the same thing. So I start this, and I start my experiment. And then I can do my metrics here. You can select the metrics. So I want to profile an application, and you can put your target, you can put your directories, you can put your parameters over here. Same thing. It's nothing. It's not any different. I'm just not in a habit to use the GUI. So And I can put it in my code too. So I can just, every time I'm running that benchmark, I can use collect and then just keep it in my code, in my benchmarking code. And so this is the GUI for that. Any other questions? Yeah.
How intrusive is the tool? How big are the logs that it collects?
Yeah, it's pretty intrusive because so it will not affect your inlining decisions if that's the level of detail that you want to go. But if you're doing comparison, it's going to affect both your experiments the same way. Will it tell you your hotspots? Yes. Will it tell you? Is that my phone? Yeah, sorry. People just don't know I'm here, I guess. So, what was I going to say? So, but it's a needed tool because application profiling is not being done right by other tools. This is the only tool that I and many like me, very serious performance engineers, would use. And the reason we do that is because the method of profiling is different in here. So there's async and sync profiling methods, and so anyway, that's a different subject. But there's a lot of talks on that. What are the right profiling tools to use? This is the only profiling tool that I have. There's also like tools. Like Richard Warburton has one where he does this, but it's a more like a command line thing. It's not as sophisticated as this one. But there's a team dedicated to get inputs from you to make sure that it's working for you. So, and I've worked with them for such a long time within Oracle, within Sun, and now outside as well. Very helpful. The studio analyzer team is very helpful. And again, going back to intrusive, when you're doing performance analysis, you need a way to look into your code and make sure you're measuring the right thing, you are seeing the right thing happen, right? Now, at that point, I'm not doing it in production, right? I am doing it outside. I'm doing it outside production. Yes, it's intrusive, but do you know of any other way to do it? No. So, and I don't either. So it's not like garbage collection logs. So you print GC details. It's not that intrusive at all. So you can have it in production. This you cannot have in production. This is for making sure your problem statement is viewed correctly, or you have a problem and you want to get to the bottom of the issue. So you want to use this tool. So it is when you need to work and look at the code and make sure you're doing the right thing. You could use it at OS level. You could use it at any, like I said, it's a platform level tool. So you have to make sure that that's one of the things that you need to make sure that is, you're looking at the right thing and you're confident about the results. So, I mean, these are not, like I said, they're different tools. So if you talk about overhead, a lot of tools will have more. But the more information you get, this one gives you call stack. This one gives you experiment information. The more information you have, the more overhead it is, right? So yes, it's got a lot of overhead. Oh, how much log do you need?
Yes, but I saw that this test, it's run for about a quarter an hour, something like that.
Yeah.
So how large are the log? How much disk do I need to use the tool?
Okay, so that's a good question. My theory is that if I'm using this for a customer, I will not use it for more than not run it for more than 10 minutes. Actually, many times, about 5 minutes is good enough for me. All you have to do is make sure it's in steady state. Your application is in steady state. This is a benchmark. It's a micro benchmark. It's just doing one specific thing. So for me to get as much information, it's better. So to show you 29 seconds versus 19 seconds, I have to run it for that long, right? If I showed you 0.000 versus 0.0001 or something, you're not going to appreciate that. So I have to run it for a longer time. But so when I'm looking at customer applications or when I'm looking at some platform changes, I'm going to make sure that it's less than 10 minutes. So the logs at that time would not be as heavy as these. You'll still see the same information, but it's not, you know, when I showed you the experiment, you saw this density of events. You won't see that if you only have 5-minute window. Okay? You will just capture the right events at the right time, and then you zoom in, and then you correlate your GC events to the regular, if that's what you're looking at. Any other questions? We have just less than a minute. So if there's no more questions, thank you very much. I appreciate you guys being here.